Hi, I will be talking about some work that I've done. I'm excited to share some of our results, and I will be talking about hunting for intermediate mass black holes and what we can learn from them. So more specifically, I'll first talk about an intermediate mass search that I've been working on and have used on LIGO's second observing run. And in the second half of the presentation, I'll talk a little bit about what we can learn from AGNs from these black hole mergers. So firstly, when we think about black holes, we think of two main groups, stellar mass black holes and supermassive black holes. And since the 70s, we've managed to accumulate a lot of definite evidence for these two categories, from EM observations, direct kinematic measurements, and even gravitational wave events. However, even after 50 years, we only have a handful of candidates and one confirmed intermediate mass black hole, the black holes that lie between 100 and 1 million solar masses. Now, if we can find more of these intermediate mass black holes, we can use them to better understand how galaxies and supermassive black holes form. We can also use them to test general relativity and also learn more about how the different scenarios in which they can actually form. So there's a variety of different scenarios on how these intermediate mass black holes can form. And on this schematic diagram, I've tried to put some of them on. So on this plot, the x-axis is kind of like the component object's mass and compact object's mass. And on the y-axis, we have the redshift at which the scenario takes place. And there's many methods here, but I'd like to focus on two main methods. And so the first one is from population 3 stars. And so the idea is that when the universe was very young and assuming low metallicities, huge population 3 stars with like masses above 200 solar masses might have formed. And due to these low metallicity environments, these stars might not have lost a lot of their mass from winds, and so could retain most of their mass up till the end of their lives, at which point they could undergo a direct collapse into an intermediate mass black hole. And now the second scenario that I'd like to discuss is from successive mergers of black holes. And in this idea, you could basically have these these binary systems form into a larger black hole. And eventually, even these black holes could then merge to form an even bigger black hole, like an intermediate mass black hole. So here you can have these binaries above me having like, which are the remnants from another binary merger, have about 60 solar masses. And the final black hole would have, a mass that's in the intermediate mass range. And what makes the scenario more tantalizing is the discovery made by LIGO in 2019. So in 2019, LIGO detected a gravitational wave event called GW 190531. And this was from the merger of a binary system that produced an intermediate mass black hole of around 150 solar masses. Now, on the right side of this slide, so right above me, we have a plot of the component black hole masses. So on the y-axis, we have the secondary mass, and on the x-axis, we have the primary mass of the component black holes that merged and were produced gravitational waves, which were detected by LIGO, the LVK collaboration, and the Institute of Advanced Study, IES collaboration, which is a group outside of LIGO. And firstly, you can notice that there's also these small, tiny green, orange dots. And so these are candidate events. So these were candidates, but they weren't really considered true events because they weren't loud enough in a way. But even from this plot, you can see that 190521 has like the highest component masses as well from the various other events that we've seen. But if you look closely, we see that some of these orange guys, some of these orange candidates also have very large masses. And in fact, some of these could also form into intermediate mass black holes. But sadly, we have a tough time in LIGO, like looking at these high mass events, because these high mass events have very short durations. And so they're actually a little bit hard to have a lot of, like, it's hard to see them in all the data that we have in a way. And essentially it's because, so this is a schematic plot of a signal's duration on the x-axis and the signal's mass on the y-axis. So as we go up in mass, we eventually have shorter and shorter durations of a signal. And so when we reach the intermediate mass range, which is like above 100 solar masses, the signal is very, very short, and it's like a fraction of a second. And this wouldn't be a problem, like finding these really short events in the data wouldn't be too problematic if all we got in the data was just signals and noise. But it gets a little trickier than that because we have a lot of glitches in our data. Now, glitches are these random sporadic noise artifacts that occur in the detectors. And these could occur from things such as closing a fridge door and a variety of other things. And a lot of these other things that could create glitches are still unknown. The spectrograms on the bottom of the slide are frequency time plots of the detector data. So here on the left side of this slide, we have spectrogram of a glitch in Hanford, and in Livingston, there was nothing happening. So it was just like blank in a way. So this is an incoherent glitch. It's only present in one detector, so it's incoherent. Now on the right, we have the signal from GW 190521, which is that IMDH that we looked at a few slides back. So here we can see there's a spectrogram of the signal in both detectors. And again, the signal is the signal is coherent because it's observed in both detectors. But you can also notice that the morphology of the signal and the morphology of the glitch are kind of similar in this high mass regime. So the short duration, basically the short duration incoherent glitches look very similar to these high mass signals. And that makes it a little tricky for us to actually look for these high mass signals in our data because we're scared that we might be looking at glitches and thinking that they're these high mass signals. So essentially we need a more sensitive search that can better distinguish these glitches, these short duration glitches from these high mass signals. And that's kind of where my work comes in. So my search targets the binary black hole systems that have total masses above 50 and below 400 solar masses. And 400 is like kind of the upper boundary of LIGO. So that's kind of where we ended our search. And the core of my method uses Bayesian hypothesis testing. And so in Bayesian hypothesis testing, we have some data, D, and a hypothesis, H, to describe the data, and a prior about the hypothesis, which is given by pi of H. So we can, initially, when we have just our hypothesis, we have some prior beliefs on how likely a hypothesis is, and we can kind of visualize it with this scale here. So our prior for hypothesis 1, pi 1, has some weight, which gives to the hypothesis in a way. And so initially, we believe in hypothesis 1 more than hypothesis 2. So we believe in this green hypothesis more than this blue hypothesis. Now, once we get some data, we can use the data and we can analyze it with our hypothesis. And we can build this thing called evidence, which is basically the probability of the data given the hypothesis, right? And so that kind of shifts our understanding of which hypothesis is more likely given the data. Now, combining the prior and the evidence together, we can build what's known as the posterior, which is kind of giving us like the true belief in our hypothesis given the data. And we can use this posterior probability to then understand which hypothesis is favored. So in this case, we see that with the prior and evidence, hypothesis 2, the blue hypothesis, is heavier than the green hypothesis in a way. And so here, hypothesis 2 is being favored. And we can quantify how much it's favored by using this thing called a Bayes factor, which is kind of like the ratio of the evidences. And here we see that the Bayes factor for the hypothesis 2 compared to hypothesis 1 is much larger. So this is kind of the core idea behind my, my search. And so what we do is we're looking at the hypothesis of if data has a signal, if the data has a glitch, or if the data has just noise. And we're kind of combining the evidences we get and the prior probabilities for these in this, this one kind of ratio number, which is called the BCR, the Bayesian coherence ratio. And It looks kind of complicated, but essentially what it could be thought of as is kind of like the ratio of the probability that something is coming from a coherent signal versus the probability that it's coming from an incoherent glitch or just noise. Now, using this tool, we can try to start looking at background data, foreground data, and simulated data. So foreground data is kind of like the data which is taken from 2 or more detectors at the same time. Now, the things that we find in the foreground data can be from real astrophysical signals, but it could also be glitches in the data stream, or it could also just be noise. Now, we also have this other category of background data. So background data is data that basically just doesn't contain any signals, and we know it doesn't contain signals. And we also have simulated data in which we have the foreground the foreground data, and we make sure that there's no candidates or events, and then we kind of simulate an event and inject it into the data stream. And so we know that when we analyze the simulated data set, we're finding only the injected signals. Okay, so with these data sets in mind and our BCR tool that we've discussed, we can actually now try to figure out if some of the candidate events that were picked up by LIGO are indeed true signals or glitches. And we can do this by calculating a probability, by assigning a probability of how astrophysical a candidate is. To do that, we use this plot on the right of the slide. So this plot is a survival probability plot. And on the x-axis, we have the log BCR, which is the tool that I discussed. And on the y-axis, we have the survival probability. And on it are plotted the survival functions for the simulated data in blue, the background data in gray, and some candidates in orange. The vertical lines represent the candidate's BCR value. So what this plot kind of tells us how likely, so if we take a BCR of -10, right? So we take a BCR of -10 and we go up, we see that at -10, the gray distribution has a survival probability of 0.4. And that means that after a BCR of -10, only 40% of background data survive in a way. So we can use the same concept to then look at these foreground candidates. So take this one, GW170814. So GW170814 has a BCR of around 20, and we see that there's no background data with like BCRs above this point. And so in a way, we can kind of start like use this concept to try to build a probability of how astrophysical this is. And so GW170817 lies far from the background, while GW170817A lies kind of on the background. We see that 10% of the background events still have BCRs greater than GW170817A's BCR value. So we use this tool to kind of like look at all the various events from all the data from the second observing run, and with it we kind of we calculate our p-asters for all the different candidates, and we found one new candidate, which was GW170222, and so this ended up being like a vanilla kind of binary black hole system with solar masses of like 30 on 30. And we also found that all of our p-astros that we calculated with the BCR matched up with the LIGO Virgo Kagra collaboration's p-astros for their first binary black hole catalog. What's also kind of exciting and interesting is that our p-astros match up with those from the Institute of Advanced Study events. So the Institute of Advanced Study made their detections kind of separate from LIGO. They did their search separately from LIGO using their own pipelines and data analysis and detection techniques. And so it's been kind of uncertain in like the community if we can trust these IIS events or if they're not actually like events, and they might be something else, some glitches or something. But I think after the study, I have more belief in these IIS events because we're also reporting a very similar probability of these things being astrophysical. So yeah, I believe that a lot of these things could have astrophysical origins. So this brings me to the second half of my presentation. And I'd like to talk about what we can learn from active galactic nuclei from mergers of binary black hole systems. Okay, so first of all, a normal typical galaxy is one where most of the light comes from the stars in the galaxy. And an active galaxy is one in which most of the light comes from a point-like nuclear source at the center of the galaxy. Now, this bright compact region at the center of the galaxy is called active galactic nuclei, or AGN. The main model we use to look at AGNs is shown on this slide. In this model, active galaxies contain a supermassive black hole at their center. Now, as surrounding galactic material moves towards the center, material forms an accretion disk around the supermassive black hole. And friction in the accretion disk can start to slow the material enough to cause the material to fall into the supermassive black hole. And this causes the inner parts of the accretion disk to become very hot. The hot part then can produce jets of gas and radiation that streams out of the nucleus along the disk's axis. These jets are actually observable at radio wavelengths. And if the disk is really thick, then these jets can be really culminated into focused narrow beams. And such jets have been observed in active galaxies. And for example, in the center of M87. So this was shown on the previous slide. So M87 is the galaxy on the right side of the slide. And that line-like structure is the jet coming out of M87. So although there's a lot of different components in this model of this active galactic nuclei, I'd like to focus close towards the center of this model, towards the supermassive black hole and the accretion disk next to it. So if we zoom in on that region, we can kind of break it up into two main components. We can break it up to spherical component and a disk component. So the spherical component has a bunch of these stellar objects, stellar remnants and stars, and the disk has the accretion disk, and it has some embedded compact objects in the disk itself. And these compact objects can have a lot of different type of interactions. The black holes embedded in the disk can migrate inwards, spiraling closer into the supermassive black hole. And as they migrate, they can form binaries. These binaries can be disrupted by other stars and compact objects that whiz by. The black holes in this disk can also accrete gas from the disk that they're in. And the accretion actually helps the black holes kind of get torqued, can torque the black hole spins. So lots going on. And from all this stuff, we have quite a few observables from AGNs. So we have a broad range of luminosities, we have jets, as we discussed, and we actually also have, in a way, a unique set of gravitational wave emissions that we might see from AGN disks. And this is kind of what I've been working on, looking at the gravitational wave emissions from these black hole mergers in AGN disks. So to understand the gravitational wave emission, let's take a step back and try to put together what we expect to see when these binary black hole systems merge. So we can start by just initially thinking about initially you can just place some compact objects in the disk, right? These compact objects would start spiraling inwards with type 1 migration. And that basically says that bigger objects will migrate faster, and the thicker the disk, the faster the migration. And so as the migration process, as the compact objects start migrating, they might have some random encounters, and they might bump into someone else's gravitational sphere of influence. And this might cause them to form binaries inside the disk. And there will be a bias towards heavier objects, because these heavier objects are the ones moving faster. The heavier object will more likely form these binaries. And so this brings us to step 4. So once you have the binary, you can start making the binary shrink in size and become smaller and smaller due to the gas hard. So gas in the disk can torque the orbits of the objects and drive them closer together. And there might be a point at which, if the binary is moving too fast, gas hardening might not be as effective as dynamic hardening, which is kind of when you have a binary system and another compact object whizzes by, the binary might get hardened and tighten up. And so these factors can help bring in the binaries close together and merge within the lifetime of the AGN. And from such models, we can expect to see that the lower and upper mass gap in the compact object spectrum, mass spectrum, will get filled up due to the mergers in these disks. We can also expect intermediate mass black holes to form at migration traps, which are kind of like rings in the disk. So they're kind of like rings in the disk where the outward radiation pressure from the supermassive black hole balances out with the inward migration pressure. And so it becomes like this like ring of like a trap almost where these compact objects can get stuck. And finally, we have unique spin distributions for these black hole binaries. Oops. Okay. So in old AGNs with dense disks, we expect the orbital angular momentum, the white arrow on these small binaries that I've drawn, and even the component black hole spins, the blue arrows on these small black holes, to align with the supermassive black hole and the AGN disk. And this is essentially because in these older AGNs, firstly, most of the compact objects that were in the sphere get kind of squashed down into the disk by this age. And additionally, the black holes in the disk themselves have a lot of time to actually get torqued into alignment with the disk. On the other hand, when we go to younger and thinner disks, there's a lot more dynamic interactions. There's a lot more stuff in the sphere and there's a lot more dynamic interactions. And so every time it's like a third wheeling party passes by a binary system, the binary's orbital angular momentum, it kind of gets thrown off. So that's kind of what I've tried to show on this small schematic plot. I mean, this diagram, you see that the white arrows are kind of like pointing all over the place. While on this one, they're all aligned. You can also notice that here, the blue arrows are kind of also pointing all over the place. And that's because, again, because the disk is so thin, these component black holes haven't had enough time to create, haven't been able to get torqued enough by the gas to align with the supermassive black hole. So we have these two different edge cases in a way, but we also have this like middle cage, these like dense middle age AGNs, which have like ages between the two, but still have dense disks. And in this type of AGN, you'd have really unique spins. You'd have you'd have enough gas for the black hole, component black holes to get aligned with the supermassive black hole. But because you still have a lot of these dynamic interactions, every time there's a dynamic interaction, the binary orbital angular momentum can get thrown off. So in a way, what happens is that you have your binary, right? And the third guy comes and disrupts the binary and it'll cause the angular momentum to get kind of thrown around. And so you might end up having a binary that starts spiraling like this or like this. And so basically the component black holes are still pointing up, but the orbital angular momentum would point in random directions. And this type of orientation of the spins is kind of unique. So if we can measure systems with such spins, we might be able to better understand the interactions in these AGN disks. And so at early times when these binaries are far apart still, we expect that we can study these the population of the spins, and we basically need to keep in track of two angles: the angle θ1, which is kind of like the angle between the orbital angular momentum and the primary component black hole spin, and θ1 2, which is the angle between the two black hole spins. And the plot on the right kind of shows what the binary black hole spin distributions we might get from binary black hole systems from different AGNs. So the x-axis, we have the cosine of θ1 2, and on the y-axis, we have the probability density. So if you look at the blue curve, we see that most of the probability lies near cosine theta of 1, meaning that the component black holes are kind of lined up. they're like often aligned. And if you take a look at the green distribution, we see that the green distribution kind of says that the cosine theta distribution is uniform. And what that means is that it's likely for the theta 1, 2 to for the component black holes to be pointing in any kind of direction. To shift from this blue distribution to the green distribution, we can actually just use we can just adjust the sigma for a Gaussian centered at 1. And so as you adjust sigma, as sigma becomes bigger and bigger, you see that the distribution shifts from that blue vertical line to that green horizontal line. So we basically have a sigma as a parameter that describes how our spin population can change for different AGNs. With this in mind, we can begin to ask certain questions. We can try to, first, we can try to answer what we can learn about AGNs from measured sigma 1 and sigma 1, 2 values. We can also try to look at the fraction of events that could come from AGNs. So after looking at all the gravitational wave events so far, we kind of so this plot has been made using all the gravitational events that LIGO has detected so far. And I'd like to bring our attention to this region of the contour plot. So this basically says that sigma 1 is likely to be near 0. And so that means that the component black hole 1 should not have any sigma. And so it's most of its black holes should be aligned with the AGN disk in a way, or with the orbital angular momentum. And we see that sigma 1, 2 says that it does not have any weight on sigma 1, 2 being 0. And so this is saying that because sigma 1, 2 is not 0, it's saying that the data prefers that the black holes are more in a way separated. And so if we kind of like trace this back to our conceptual model of what AGNs could look like for different sigma, we can piece together that this kind of our current results kind of show that we do not prefer old dense AGNs. There are some next steps that we'd like to do. So currently our model has some assumptions that do not allow the spin to evolve with time. So we're kind of like fixing the black hole spins, but this is something that we're working on trying to improve. And we would also like to try to like remove out events that would more likely not come from AGN disk, like the lower mass events. Finally, we can also try to look at what fraction of events come from AGNs. So we can use a Mishra model to do this. So we can basically like have a model for AGNs and have a model for field binaries and have this Xi parameter, which is kind of like telling us how many events we expect to come from AGNs and how many events we come from the field. And we can try to analyze our data with this model and see what values of Xi we get. And so we see that we kind of rule out the possibility of Xi equaling 1. So there's no probability weight for Xi is equal to 1. And so that basically tells us that it's unlikely for the merges that we've seen so far to just come from AGNs. So in summary, we have some preliminary results for our AGN population study. And we would like to reparameterize our model to use different spin parameters, ones that won't really be affected with time. And for our intermediate mass search study, we've found one new vanilla binary black hole candidate, and we've seen that our results in a way match up with those from the IES group and the GWTC LIGO study. Thank you.
Great. All right.